Hi Math 30s. This video is going to be on lesson 2 on page 448 of your workbook, and we're going to be analyzing the graphs of radical functions. So essentially taking a function and putting it underneath a radical sign. How I'm going to start though is with two examples that are not in your workbook. So if you want to look at this first example here, we are given the graph of a linear function, and they're calling that function g of x. And we're going to sketch the graph of the radical function. So taking g of x and putting it underneath a radical sign. We can actually get the domain of the radical function by just looking at the original function. So here's how we would do this. What you want to do, if you're asked for the domain of the radical function, is you always want to look at the original function, and you want to look at the piece or pieces of the graph that are greater than or equal to 0. So essentially, the piece of your graph that is above the x-axis. So I actually have that right here. So the piece of the original graph g of x that is above the x-axis, greater than or equal to 0, would be from -1 onwards. Okay, this will give you the domain of your radical graph, just looking at that piece there. And the reason why we always want to take the piece of the original graph greater than or equal to 0 is because we know we cannot take the square root of a negative number. And with radical graphs, we're always going to be taking the square root of the y value, so we can't have any negative y values. So if I said, without even graphing the radical graph, what would the domain of that graph be? The domain would be x is greater than or equal to -1. So the domain of the radical graph, x is greater than or equal to -1. Okay, let's sketch the radical graph now. So when we're sketching the radical graph, where you always want to start is at the invariant points. On radical functions, invariant points will always occur where y is equal to 0 and y is equal to 1. So you want to mark those invariant points on your original graph because they will be also on your radical graph. So this is an invariant point here because y is equal to 0, and this would be an invariant point because y is equal to 1. So those are your two invariant points. From here, you're going to choose some other points from the original graph where that original graph is greater than or equal to 0. So I'm going to choose this point right here on my original graph. So that would be when x is -0.5, the corresponding y value is approximately 0.5. And then we're going to find the point on the radical graph. I'm going to take this point right here. So when x is 2, y is 3. And then I'm going to take this point right here. When x is 3, y is 4. How we find the corresponding points on the radical function is we take the square roots of the y values. So on the radical graph, my new point would be -0.5, so it's the original x point, and then the square root of 0.5, and that's going to be your new y coordinate. So if you look here, I've got that on our calculator. Square root of 0.5 is approximately 0.71. So let's write that down. Okay, so this point here is going to be slightly above the graph of y is equal to g of x. Then next we're going to take the square root of 3. The square root of 3 is about 1.73. So on the radical graph, my new point will be 2 and 1.73. Okay, so that would be about here. And then the last point that I have, it's going to be 3, 2. The square root of 4 is 2. And that would be a nice point that I know, which is right there. What you then want to do is you want to join your coordinates with a nice smooth curve, which is a little bit hard to do. And then what you have is you have the graph of the radical function. And if you look, and I said, what's the domain of the graph of this radical function? The domain is the set of values greater than or equal to -1. If we look at the next graph, so here I've given you a quadratic. We don't have the equation of the quadratic. We don't need the equation. And we're going to take this quadratic, which they're calling now f of x, and we're going to sketch the graph of the radical function. Again, let's start with the domain of the radical function without graphing it. How we do that is we are going to look at the domain of the original function. So the original function is my quadratic f of x, and we're going to look the piece or pieces of the graph that are greater than or equal to 0, because we cannot take the square root of a negative number. So where that would be, I'm just going to use a highlighter to show you this. It's, remember, any of your piece of your graph that is above the x-axis, and that would be this here. So if I just mark it, the domain of my radical graph is going to be x is less than or equal to -3, greater than or equal to -7. That would be the domain of this piece. So the domain of my radical function would be x is less than or equal to -3, greater than or equal to -7. Okay, from here, let's sketch the graph of the radical function. So again, always start by marking your invariant points. Remember, on radical graphs, invariant points are where y is 0. So I've got those points already here. And then where y is equal to 1. So that would be here, and that would be here. Now I need other points on my original graph. So I'm going to take this point here, which is x is -6 and y is 3. So this point here, when x is -6 and y is 3, I'm going to take this point on my original when x is -5 and y is 4. And then I'm going to take this point for my original when x is -4, y is 3. To find the corresponding points on my radical function, remember we take the square root of the y values on the graph. So on my radical function, I'm going to have a point at -6 and the square root of 3. And the square root of 3, again, is approximately 1.7. Then I'm going to have, let's just actually mark that. So -6 and 1.7 would be about here. Then I'm going to have a point at -5 and the square root of 4, which is 2. And then -4 and the square root of 3, again, approximately 1.7. And you're going to join these points with a nice smooth curve, and the concavity of the curve, it's called concave down. Calculus is going to explore concavity. But that is what the graph of your radical function would look like. And then again, if we compare that to the domain that we had originally found, it matches. The domain is less than or equal to 3, -3, greater than or equal to -7. In interval notation, this would be your domain. So now that you've seen that, we could go and look at some of the workbook questions. So just go to your workbook and flip a few pages. I want you to go to this page here. So go to page 449. What I often like to do with radical graphs is I create something called a red zone. And I didn't do this on the first two examples, but I will do it from here on forward. So what the red zone is if you have a pen and a ruler, I like using a red pen, you want to draw a horizontal line going through y is equal to 0. And you always want to draw the line going through y is equal to 0 and y is equal to 1. How the red zone works is as follows. This is our original graph here, and the original graph was a linear graph, right? Y is equal to x plus 1. Remember that we always place our points, the invariant points would be at when y is 0. So this is where y is 0 and where y is 1. From here, when you're doing your graph of your radical function, if you're within your red zone, the graph of the radical function is always going to be above your original graph. And that would be this here. Once you're outside of the red zone, this is your original graph, and your radical graph will always be below the red zone. So this red curve here, that's the graph of the radical function. So I'm going to show you that with the second example, and then hopefully you'll start seeing what I mean by doing this red zone, and we'll do it again in any class examples going forward. So again, with a red line and with your ruler, draw two lines going through y is equal to 0 and y is equal to 1. You then go to your original graph, and the original graph is going to be the thinner line here. It's the absolute value of x is the original graph. And you put your invariant points in. Where are invariant points? Invariant points are always going to be when y is 0 and when y is 1. They will be on both the graph of the original and the radical. Then, when you're within your red zone, so this is within the red zone, here's my original graph. Your radical graph will always be above the original graph within the red zone. Okay. Then when you're outside of your red zone, when you're beyond the red zone, your radical graph is always going to be below your original graph. And this will help a lot with your sketches when you don't have the equation and you cannot verify on your calculator. So let's apply that, and let's look at class example 1 here. So it gives us the graph of a function, y is equal to f of x, and it says sketch the graph of the radical function, so put f of x underneath the radical sign. First, take your ruler out, put your red zone in. So draw your horizontal lines going through y is equal to 0 and y is equal to 1. From there, mark your invariant points. So invariant points are going to be all the points where y is 0 and y is 1, because those are going to be points on your radical graph as well. Once you have all of those invariant points, I'm going to follow that rule of the red zone. If I am within the red zone, so this would be within the red zone, the graph of the radical is going to be above the original. And you always do it with a nice smooth curve, and that would be, it's called a concave down curve. I go over here, and I say I'm within the red zone. Connecting these 2 points, the graph of the radical will be above the original with a nice smooth curve. Same over here, it's going to be above the original, and here. Within the red zone, nice smooth points above the original. Here I'm outside of the red zone, so all of my points are going to be below the original. So what you want to do to get the points on your radical graph is you want to take square roots of nice numbers. So for example, this is 4, and I know that the square root of 4 is 2. So remember, it's always your original x-coordinate, and then it's going to be the square root of the y-coordinate. So this point on my radical graph is going to be -1 root square root of 4 is 2. This point, it's going to be 0, the same x point, and the square root of 4 is 2. This point, square root of 4 is 2. Square root of 4 is 2. Okay. So I'll, with a nice smooth curve, try to get up to here, and then I'm going to have a straight horizontal line going through these points here. What we could do is this point here is at 3. The y value is 3. And we know that from the previous example, the square root of 3 is approximately 1.7. So that would be out here, right? This would be at 2, the square root of 2. Let me see if I have that on the calculator. Square root of 2 is 1.4. So here, when y is 2, the square root of 2 is going to be about 1.4. So again, you're going to try to, as best you can, connect these points. The nice smooth curve. And I'd use a ruler here. Okay, obviously I need a ruler. Then you're going to connect again. Nice smooth curve. And it's just going to be really difficult for me to do from here. Okay, that should be a nice smooth concave down curve. Over here, that value is 2. And the square root of 2 we said was 1.7. So we'll go about here. So again, starting here, you draw your curve. And again, not quite. Okay, pretend it just is going through. Yeah, it looks terrible. But I think hopefully you understand what it's supposed to look like. Okay, let's answer these questions. It says state the domain of the original function. So the original function, this went to infinity to negative infinity. So the domain of f of x would have simply been xer. The range of the original function, the biggest y value was 4, and then it went to negative infinity. So the range would be y is less than or equal to negative 4. Looking at the domain of the radical function, remember that we look at the original graph and we only care about the piece or pieces that are greater than 0, that are above the x-axis. So if I'm looking at my original graph, I'm just looking at these pieces here. The domain of the pieces above the x-axis would be from 16 to negative 3. So just doing this in proper set builder notation, x is such that x is less than or equal to 16, greater than or equal to negative 3, comma xer. The range of the radical function, the biggest y value is going to be when we take the square root of 4. So if this is the biggest on the original function, the square root of 4 is 2. That's going to be the biggest y value on the radical function. And the range is going to be from 2 to 0. Okay, let's look at this last class example. So now we're given the graph of g of x. Okay, so this is the graph of g of x, and it wants us to, it says, what is the domain and range of the graph of h of x? And h of x is going to be placing g of x and making g of x, putting it under a radical sign. So it says don't sketch it, but I find it's often helpful to sort of visualize what sketches would be. So we don't have any red zone here, right? So this is my red zone because this y value is 3. So I can't apply that going above the original in the red zone and then below the original outside the red zone. There's nothing in the red zone. So what I need to do is I need to look at certain points on my original graph. So this point here on my original graph, 0, 6, what would that point be on the radical graph? On my radical graph, it would be at 0, the square root of 6. So the square root of 6 is 2.4. So the y value would be 2.4. I know that this is 3, right? They're telling me the y value there is 3. So 2.4, I'm going to say is about here, right? So that point would go down to 0, 2.4. 2, 9 is going to become 2, 3. And I know if that's 3, it'd be about here. This point, 6, 3, square root of 3 is what? 1.7. So that was 2.4, that was 3. So it's going to be at 6 comma 1.7, which would be lower than that 2.4. So let's just say that's here. This point here, so I don't know what the x value is, but I know that the y value right here is 9. So if I take that point on the original, I say, okay, well, what's the point on the radical? I know that if the y value is 9, it's going to be the original x and 3, which would be here. And then again, this point on the original, what's the point on the radical? It's the original x. If the y value is at 9, it's going to be at 3. We're above the red zone, so all of these points are going to be below the original graph. So if I connect these points with nice smooth curves, the radical function would look something like this, except for this point. That would be -2 square root of 3, which was at 1.7. So sorry, I'm forgetting this point. There. That would be the graph of the radical function. Okay, now we could do the domain and range. So we know that this is g of x, right? The entire graph was greater than or equal to 0. So since g of x, the original, was greater than or equal to 0, sorry, was greater than 0, for all values of x, the domain of h of x, which is going to be its radical graph, will be xer, right? And if I look at my domain of my radical graph, it is going to be xer. Okay, the range of the radical graph. What you have to do, so the range of the radical graph, which is going to be h of x, we need to look at the minimum value on the original graph. The minimum value on the original graph was right here. The range is the y values, so we were looking at 3. And on the radical graph, it's going to be the square root of 3. So you always look at the minimum value, and min value of g of x is equal to 3. Therefore, the range of h of x, that point on the graph of h of x is going to be the square root of 3. So the range would be y is greater than or equal to the square root of 3, which is what we have here. Let's look at this last one. Again, here we could get our red zone in. So let's put our red zone in. There's y is 0. And we're just going to approximate where we think 1 is. Let's just say it's there. Okay, let's do the domain of our of our radical graph without even, again, graphing the radical. So the domain is going to be h of x. Remember, we look at the piece or pieces of the graph that are greater than 0. So that would be this piece and this piece. That's going to give us the domain of h of x. So that piece is going to be, there's 2 pieces actually, so x is such that the first piece would be, I'm going to give the domain of this piece, which is x is -2, and here x is -3. So it's going to be x is less than or equal to -2, greater than or equal to -3, or the domain of this piece. And this piece is less than 8 and x is greater than 3. And then comma, write your XCR. That's going to be the domain of my radical graph. Okay, if we were to do a quick sketch of the radical graph, even though it asks us not to do a sketch, it's always nice to visualize. Put in your invariant points. So all of your y is 0 and your y is equal to 1. These are all going to be invariant points. They actually give us nice points to find the graph of the radical function, because the graph of the radical function, it's going to go through 6, 2, because the square root of 4 is 2. And then here, it's going to go through -3, and the square root of the square root of 9 is 3. Remember that when you're within the red zone, you go above the original graph. When you're outside of the red zone, you are below the original graph. So that would be the graph of the radical for this piece here. Again, when you were within the red zone, you were above the original graph. And then outside of your red zone, you're going to be below your original graph. And that would be the graph of the radical. If you were asked now, what is the range of this function? What you want to do is you want to find the max value of g of x. So the max value of g of x is 9, right? So let's write that down. So on the original, max of g of x is equal to 9. What that means, the max value of h of x is going to be the square root of 9, which is 3. So this point here is going to be the max value of h of x. And my range would be the biggest y value is 3, and the smallest is going to be 0. So the range of h of x is going to be y is less than or equal to 3 and greater than or equal to 0. That will be your range. Here are your homework questions that you could work on.